This video contains the solutions for the first two of your first packet of vector free response problems. Those happen to be the first two problems from 2002, a good year for vectors. The first one is number 3 here, and they've given you quite a bit of information. They've given you the graph, the XY graph of this path of a roller coaster. They've given you the parametric equations that describe that curve, and they've also given you the derivatives. So they really want us not to mess up just because we didn't take the derivative right. And I guess probably their main concern was that we might have botched the product rule on this. So anyway, given us a lot here. You don't usually get this much. You usually just get the equations or the derivatives or something else. Alright, so first one, find the slope of the path at time 2. Now notice that there's no way, there's no indication here. There's no way for us to figure out like where time 2 is. That's certainly not, like, don't get confused and think that's where x equals 2. This is at time 2. So what we need to do for 3a, we're trying to find dy dx, that's the slope, at time 2, right? So we have, we know that dy dx is equal to y prime of t over x prime of t, right? That's the same as dy dt over dx dt. I'm writing them like this because that's the way they wrote them in this problem. So that's 20 minus t times sine t plus cosine t minus 1 all over 10 plus 4 cosine t. I got that all down, right? And this is a calculator problem. Your way of remembering the what's calculated and what's not, in case it's not clear to you, should be clear to you that you need your calculator for this, right? But anyway, in the old days, up until 2 years ago, the 1 through 3, those were always the calculator problems, and 4 through 6 were always no calculator. Now 1 and 2 are calculator, and 3 through 6 are no calculator. Let's check my mode here. I am in radian mode. Alright, so I want to do 20 minus 2, I'm plugging that 2 in here. Let me just do, so that's 18. Actually, it's going to be the big top of a giant fraction, so 18 times the sine of 2 plus cosine 2 minus 1. Right, that's the top, and that's all over 10 plus 4 cosine of 2. And certainly I'm going to write that down because if you only make a calculator error, it will only cost you probably one of the points. So dy dx at 2 rounded to 3 College Board decimal places is 1.974. Part B. We want to find the acceleration vector of the car at the time when the car's horizontal position is x equals 140. Well, x equals, I don't know what, I think the first thing we have to do is find that, right? So at x equals 140, I think we want to plug in at x equals 140, that using the very first equation, that would mean 140 is equal to 10t plus 4 sine t, right? And we want to solve for t. This is not an equation you can solve without a calculator, so I'm going to go ahead and graph that. I'm going to go back to my y equals, get that out of there. So I'm going to graph 10x plus 4 sine x minus 140, right? And then I'm going to go ahead and go to the window here. I'm interested in x values. These are the t values, right? It's between, so the times I'm looking for are between 0 and 18 seconds. So 0 to 18. And I'm interested where it hits where it's 0. So there we go, right there. So second, calculate, find that 0. It's between, oh hey, it's between 0 and 18, right? That's my window. Only happens once. Bam, there it is, 13.647. So that happens at t equals 13.647. Looking back at the graph, that looks pretty reasonable, right? That it would start out here. This is 18 seconds. That's like somewhere its journey would be there. That looks about right. So let's see. What are we doing now? Find the acceleration vector. Okay, so now that I have the time, part B, the acceleration would be x double prime of t, comma, y double prime of t. That's how we find an acceleration vector. It's the second derivatives. So you could actually find the derivatives, or better yet, since we have our calculator, this is what I would recommend you do. Instead of actually finding the derivatives, since they gave us the derivatives, I think I want to know, I'm going to go math 8, that's n deriv. I want to know what's the derivative of 10 plus 4 cosine x, comma x, at, what are we supposed to plug in here? At time, I found the time right here, right? 13.647. 13.647. That's negative 3.529. Negative 3.529. And then what is math 8? What's the derivative of 20 minus t times the sine of t plus the cosine t minus 1, comma x, comma 13.647. It is a 1.226. 1.226. So there's my acceleration vector, right? Since we just wanted to have that at one particular value, there's no need to actually find the derivative, right? To find the derivatives of those, we just wanted to plug in one number. So I need to get the calculator to do it. Find the time t at which the car is at its maximum height. That would be here, right? And find the speed in meters per second of the car at this time. All right, how do we find that time? What do we know about this point? We know that dy dx is 0, right? If that's a maximum, then dy dx is 0. And if dy dx is 0, since dy dx is really dy dt over dx dt, we know that horizontal tangents happen when the top, or in other words, dy dt is 0. So I need to take this dy dt and set it equal to 0 and find the time for that. There should be actually several times, or 3, not several, or actually no. We should find, I bet 1, 2, 3, 4, 5, 6, 7, although, yeah, and they're including those. So I think there'll be 7 places where it's equal to 0, but we want this one, so it should be clear that it's that first time, first non-zero time, where the top, where the derivative of y with respect to t is equal to 0. Okay, so I'm going to clear, and I'm going to go back here, and I'm going to graph the y prime of t, so I can find where it's equal to 0. That was 20 minus x times sine plus cosine minus 1. I already have my, and look, here's all those places that we were expecting, right? Here's the 1, 2, 3, 4, 5, 6, and it looks like actually the 7th one didn't quite make it there, right? It's off the screen. But that's exactly what we expected. So we want that time right there. So second calculate, I'm looking for the 0. That looks like it's in between 2 and 4. Sorry, 1, 2, yeah, 2 and 4. There it is at 3.024. And just to be clear, I'm going to say at time t equals 3.024, dy dt is equal to 0. That's the first part of that answer. And now they want the speed in meters per second of the car at this time. Okay, so speed is equal to the absolute value of velocity, which is here the magnitude of the velocity. That's the square root of dx dt squared plus dy dt squared. Right? Find the speed in meters per second of the car at this time. But of course, since this is 0, then its speed is just dx dt, right? When you look at this, I mean, it should be clear to you that if the y velocity, if it has no up and down velocity, its speed is just this one. But notice that plugging 0 in for this just gives us the square root of that, which is just dx dt. So I just have to plug in this time into dx dt, and that'll give me the speed. So let's see, that's 10 plus 4 cosine 3.024, right? That's 6.028 meters per second. 6.028 meters per second. All right, and then last, for times 0 to 18, not including 0 and 18, there are 2 times at which the car is at ground level. There they are. Oops, sorry, that wasn't on the screen. There you go. There they are. Where y equals 0. Find these 2 times and write an expression that gives the average speed in meters per second of the car between these 2 times. Do not evaluate the expression. Okay, so first let's find those 2 times, and then we'll worry about the second part. Those are the places where y, or this, is equal to 0, right? So let's see if we can figure that out. So we're gonna, well, I mean, this should be pretty easy to figure out actually, right? Because, oh, you can do it with a calculator. Alright, so let's go ahead and, I'm just thinking you could do it without the calculator pretty easily, but we have the calculator, so why not? So I'm graphing the, just the y position and setting that equal to 0, because that's what I want to know, where that's equal to 0. Where is the y position 0? So that's that. We should still have our 0 to 18 window. So there they are, right? They're at those minimums right there. So second, calculate. In this case, your calculator might give you, you can try finding zeros, but it's just barely grazing the axis there. So I'm going to go ahead and look for those minimums. Looks like this one is between 1, 2, 3, 4, 5. Oh, let's say 5 and 8 or so. So just pay attention to the graph. Make sure it gives you the right. Yep, that's right on the spot. So 6.28. Notice that that's 2 pi, right? So shouldn't have been any giant surprise here. And that next one is going to be at 4 pi. So this happens. Find these 2 times. So y, the position is equal to 0 at t equals 2 pi, and t, you can find the other one if you want. And you can give them as decimals rounded to 3 places, that's fine. But it's at 2 pi and 4 pi. And what else do they want to know? Find an expression that gives the average speed. Well, this right here is an expression for the speed, right? So how do you find the average value of something? Well, that's the average value of a function, right? That's the average value, and to do that, remember, average value of a function is equal to the integral from a to b it's the integral of that function, sorry, f of x, from a to b, divided by how wide the interval is. This is the average value, right, of whatever. Average value. And so if we want average value of speed, that means I have to do this with this. So I want the integral from 2 pi to 4 pi, and since that interval is 2 pi wide, I have to have 1 over 2 pi on the outside here, and then of this, of the square root of, and I think probably they would be okay with you just writing this, x prime of t squared, instead of actually writing what they are. So there's your average speed right there, right? Average value of a function. All right, that was 16.5 minutes. That was a long one. All right, see if we can make shorter work of the next one. All right, we have a, this is a number 1, so we've also got our calculator active on this one. Particle moves in the xy plane so that its position at any time from negative pi to pi is given by x of t equals sine 3t and y of t equals 2t. Sketch the path of the particle in the xy plane and indicate the direction of motion. All right, I'm going to go ahead and do that with my calculator. And there's quite a bit of setup here. First we have to go mode. We want to go into parametric mode. Sorry, put that somewhere where you can see it. There, I'm in parametric mode now. And I go to y equals. And it gives me my y and my x and my y. So it's sine of 3t, and y is 2t. Now do not hit graph at this point. You need to go to the window. We want to go from times negative pi to pi. This is like a pi over 12 step or something like that, so that should be fine for us. The window itself, it looks like they're going from -2 to 2. I want my window to look just like their window. -2 to 2, and the y values go from 1, 2, 3, 4, 5, 6, 7. -7 to 7. -7 to 7. And now I'm going to hit graph. I've got everything set up just like it, and you should be able to see the direction. Alright, so it looks like it starts at, that's probably 2 pi, right? And goes, I'm going to mark those places on the axis where see here. That should be at pi. It's at 1. Your sketch doesn't have to be perfect, but we want it to be pretty good. And 2 pi, it looks like 1, 2, 3, that's at pi. Alright, so that's a kind of an outline of points. So you definitely want to have like the right number of back and forth, right? So something like that. I think that would be fine. Okay, find the range of x of t. Oh, in the direction of motion. Notice that when we graphed it, it went from low to high. So you just have to put an arrow that shows. I think you probably only need one, but it went this way. So as time goes from -pi to pi, this thing winds upward, which should make sense, right? That's increasing. Okay, so find the range of x of t and the range of y of t. So here, oops, what's that? There you go. For b, x of t is equal to the sine function. Well, let's look at this. I mean, what are the ranges for the x values? For this, it's -1 to 1, right? I mean, there isn't really any work to do there. So let's say that the range of x of t is -1 to 1, and the range of the y values go all the way from, well, we're plugging -pi and pi into this, so it's going from -2 pi to +2 pi, right? -2 pi to +2 pi. That's a real pre-calculus kind of question there. Don't see many of those on the BC test. Find the smallest positive value of t for which the x-coordinate of the particle is a local minimum. So as the x's go back and forth, this right here, that's the first one where the x-coordinate is a local minimum. And geez, we could probably do that pretty easily without a calculator, couldn't we? Because it's just a trig function, just a regular trig function. But let's go ahead and we can do it with the calculator anyway. So we want to know that is a place where the x-coordinate of the particle is at a local minimum. So we want the x-coordinate to be at a local minimum. That means we want x prime of t to be 0, right? If we want the x-coordinate to be a minimum, then we're going to set the derivative of the x-coordinate equal to 0, right? That's how we always found maximums and minimums. So x prime of t is equal to 3 cosine of 3t, and we set that equal to 0. I think I'm going to do this without a calculator. You could graph this, right? But cosine of 3t, the 3 doesn't matter, so where is cosine of 3t equal to 0? Cosine is equal to 0 at pi over 2 and 3 pi over 2, right? And the first time that this happens, we're winding from like our -2 pi, so this is like at -3 pi over 2, right? Because as these tick from -pi to pi, we're multiplying here by 3. So I think that when I get to oh, let me think about that for a second. Let's see, maybe I should be more careful. Maybe I should do it with a calculator. Let's make sure that we get the right one. It's clearly like your intuition for like this vector stuff should be that it's happening pretty early in this time interval, right? It's happening as we go through here, and as we go 1, 2, let's see if we count that, 1, 2, 3, 4, 5, 6. As we go through this period and a half of this function because of the 3 in there, then I think that we're looking at time. We could probably just divide it up, couldn't we? 1, 2, 3, 4, 5, 6. So we're dividing that. It's going to be at -5 pi over 6, right? But let's do it with the calculator. Anyway, if you follow that logic, that's great. But otherwise, if we wanted to know where this is equal to 0 on the interval -pi to pi, then we'd have to go back and graph it, and we'd have to go back to mode, go back to function mode here for a minute, and go back to y equals and do 3 cosine 3x, and we want to graph that on the window from -pi to pi, we're looking for zeros of this, right? And we're looking for when it's a minimum. A minimum is when it goes from increasing to decreasing. Nope, just kidding. A minimum is where it goes from decreasing to increasing. So that's decreasing to increasing. So right there is our minimum. So we can go second, calculate, find that 0, which is over here. Come on, little guy. There we go. And that's at negative 2.62, sorry, negative 2.618. Negative 2.618, and that's, I bet you that's 5 pi over 6. Yep. All right, so anyway, what's the speed at this time? That's the time. If we want the speed, speed is equal to the square root of dx dt squared plus dy dt squared. So in this case, that's going to be the square root of the derivative of the x is 3 cosine 3t squared, right? Plus dy dt, the derivative of y is just 2 squared. So you can go ahead and plug in cosine of 3t. We should be, I don't know, should we do this without a calculator? What's 3 times negative 5 pi over 6? That would be negative, we have 3 times negative 5 pi over 6. That's negative 5 pi over 2. So if you think about the cosine function, as it starts here and goes like this, we have, and of course, you should have been thinking all along, I mean, didn't we know this was going to be 0? Because didn't we find by, we set the derivative, we set that equal to 0. So of course, there's 0, pi over 2, pi, 3 pi over 2, 2 pi, and 5 pi over 2. So of course that's 0. Plus 2 squared, so that's the square root of 4, which is 2. So the speed is 2. Oops. So speed is 2. And last part, in the distance traveled by the particle from negative pi to pi, is it greater than 5 pi? Now that's asking about the actual length of this path. So let's go ahead and set up the expression. The expression for that, total distance traveled, that's equal to the integral from negative pi to pi of the square root of dx dt squared plus dy dt squared. Right, so we just found those things. We just wrote that expression down right here. Right, so let's go ahead and evaluate that with a calculator. So I'm going to go to Math 9, fn int, and this is my function. Be very careful with your parentheses here. That whole thing has to get squared. So I'm going to have the square root. That first set of parentheses just opens the square root sign. So I need another one around 3 cosine of 3t, and then close the 3t, and then close the 3 cosine, and then square that whole thing, plus 2 squared is 4, and then close the square root sign. Now that should be right, comma x, comma, I'm going from negative pi to positive pi, and that should give me the length of the curve. Calculator thinking very hard. Come on, calculator, you can do it. The screen dimmed. It takes so much brain power to do this. This ancient TI-83 has a very slow brain. In the meantime, oh, there it is. Never mind. I was going to go get a cup of coffee. So let's see. This is part D. The distance traveled is the integral from negative pi to pi of the square. You should write this down, right? Of dx dt squared plus dy dt squared, so they just know that you know what you're doing in case there's a calculator error. And that's equal to 17.973, and 5 pi is approximately equal to 5 pi is about 15.708, so the distance is greater than 5 pi. And there's our justification. All right.